Hey, everyone that's coming in. Thank you for joining. We're opening up our webinar here. We're going to wait for all of our friends and colleagues to join in. So hang tight as we wait for everyone to hop on. If you are looking for the Preventing Critical Misses in Defect Detection, a data-centric approach with MongoDB and Voxel51, you are in the right place. So hang out. We'll be getting started in a second. I am joined here too with Robert from MongoDB, as well as Kirti and Patricia from the MongoDB team as well. They'll be helping out on the chat side. A couple things and house cleaning before we get started. We want to make sure that this is a fun, engaging event throughout the entire webinar. So if you do have any questions or you want to chat about whatever topics are going on, feel free to make sure you put your messages in the appropriate spots. We just ask that if you do have a question, maybe about something that someone brought up, or you just want a little bit more clarification on something, feel free to drop that in the Q&A widget. It's on that Zoom bar on the bottom there. Might be a little bit difficult to find, might have to hit the three dots to find it, but helping by putting the Q&A in the Q&A widget helps us a lot as presenters to answer your questions to make sure they get not lost in chat. But chat is good. So just the chat sometimes gets chatty. So I want to make sure that that is okay with everyone. As we get started here, a quick icebreaker as we wait for everyone to come in. Let me know where everyone is calling in from and maybe what you're up to in the CV, ML, or computer science field. Always good to kind of know what everyone's up to. Feel free to drop a LinkedIn if you're interested in networking or just kind of getting to know whoever's here. For instance, I am calling in from New York City. That's where I'm based out of today. It's a little bit rainy. It was raining earlier today. It rained a lot yesterday, but I'm based in New York City, and I'm currently in the computer vision field. I work for Voxel51, but I'm spending most of my time today on manufacturing, robotics, and some autonomous vehicle stuff. So feel free to drop that in the chat. Just kind of call in where you're from and maybe what you're doing so far. A lot of wonderful documentation, right? Danielle, I was just there the other day, so I totally feel that. One thing too, Zoom's a little weird with this. I just want to make sure that everyone can make sure that they're chatting to all their friends. Make sure you change the message to everyone instead of just hosts and panelists. Otherwise, all my friends here are just messaging me and Robert directly. So we want to make sure the chat stays chatty. Make sure you don't feel like you're alone. So make sure you change that over to everyone, and everyone should be able to see it if you like to. If you want to keep it private, I totally get it. No worries. So all good there too. Throughout the webinar, some of our colleagues will be dropping links into the chat, basically to whatever topic we're talking about, making sure that everyone's on top. There's a lot of really exciting content that we want to bring to you during this webinar, and we can't fit everything into this next hour. So we want to make sure that everyone has access to things like the GitHub repos, documentations, or pages that we're talking about. So just keep your eye on the chat as we'll kind of put a bunch of these there as we go. Oh, I was clicking on the LinkedIn link. Well, I want to make sure all my friends, I'm connect with everyone that puts their LinkedIn, and I didn't mean to open it up on the screen. I'll wait one more minute for anyone that is potentially coming in here, and then we will kick things off. Quick summary of what we're going to be going over today. Robert will be going first here. We're going to hand it off. He's going to give us kind of a nice look at what MongoDB is up to, kind of what is new, as well as kind of what they're about. And then afterwards, I'll be diving into kind of how that partnership between 51 and MongoDB has started and kind of blossomed over the last 5 years. And then we kind of nail down specifically how this affects things like manufacturing specifically. We have a bunch of code and notebook examples and visuals to look over. So plenty of different ways to learn if you're visual learning versus coding learner, something like that. A little bit of everything for someone. So I'm excited to bring it to you today. Looks like we're right about at 1:05. So I'll hand it off to Robert to kind of kick things off here and get us started. Sound good, Robert?
Absolutely. It's a pleasure to meet everyone here. As as my friend here, Daniel, has said, my name is Robert Jones. I'm an advisory solutions architect here at MongoDB. As I said in the chat, I'm here in Houston, Texas. My background is in oil and gas industry, where I did quite a lot of work in digital transformation projects, upstream data architecture, and the like. So this is definitely a topic area that is near and dear to my heart here. What I'd like to talk to you about, and I'll go ahead and share my screen as I do. What I'd like to briefly talk to you about is the role that MongoDB plays in a lot of these digital transformation projects, and certainly the role that MongoDB would often play in a lot of projects that would also be making use of Voxel51 and their offerings. So at a high level, I'm going to talk about digital transformation. Try to make this pretty quick. That way we can get in and actually see some more interesting stuff that isn't just slides, but rather some demos from Daniel, the Voxel51 team, to see all the cool stuff they have. They have the advantage that being in a visual space, they have very powerful demos. So let's talk about digital transformation and MongoDB and the role that we play in these kind of projects and initiatives. As many of us probably know, right? Digital transformation and kind of these industry 4.0 projects that really we're looking to kick off, of which there are a lot of computer vision based projects out there that fall into this space. We have quite a lot of data being produced, and we've done a pretty good job today of really getting the data from the field, getting it from our field operations. That tends to though be things like sensor data, telemetry, maybe imagery, etc. And that's all great. You know, you can use that data for some level of utility and processes, but to really achieve the next generation of industrial 4.0 use cases and capabilities, you really need to contextualize that information with other data as well. And the big problem that we've seen today, and where MongoDB is really finding a lot of traction and a lot of interest in industry, is in helping to address that contextualization problem. Because today we have many disparate systems where people store data you know, in siloed areas that's hard to access, or it gets dumped into a data warehouse. And ultimately, what that means is projects that are you know, industrial 4.0 projects really have a hard time getting off the ground, because they have to deal with trying to access contextual data throughout all these various sources. That really impedes progress, and it really holds up a lot of these new projects and their velocity, you know, from really achieving you know, business value. So why is data contextualization critical? If we kind of look at a handful of areas that we see, some of these I've worked in personally, even like can attest to, you know, whether it's production optimization, you know, asset optimization, predictive maintenance, which we'll be doing a little bit of talking about here later, or even compliance, or any number of use cases. As we build more sophisticated models, as we build some more sophisticated capabilities, it's not enough just to work on telemetry or sensor data. You need information about assets. You need information about procedures. You need information about the configuration of the current state of assets that might not be prescribed through telemetry. Maybe it's through unstructured sources. Maybe it's through documentation or daily write-ups or reports. And so all that information invariably gets stored and tucked away in different places in your organization. And so that creates a lot of friction, to the point of really impeding any ability of an organization to build industrial 4.0 projects. If we drill down into like a predictive maintenance kind of situation, we can kind of, you know, take a high level look at it here and just kind of make it more concrete. If we're doing predictive maintenance, you've got several different stages that you can kind of view the broader predictive maintenance, you know, capability through these various stages. And you know, if we look at them as, you know, predictive maintenance in the sense of failure prediction, you know, failure mode identification, maintenance procedure generation, where maybe you're going to actually be proactive in prescribing the maintenance procedure to remediate the asset, as well as guiding the maintenance, you know, maybe scheduling, you know, maintenance technicians to remediate the equipment, etc. All these things require a lot of information that's definitely not just telemetry. They'll require information about operations, information about the assets, information about maybe production schedules. You know, you don't want to bring equipment down right when you need it most, right? Perhaps you can bring it down when it's more advantageous, or where you have you know, maybe even quiet hours, if you will. So all these, you know, things help inform a really good, effective predictive maintenance capability. But again, they all require pulling lots of information that isn't just coming from like SCADA or traditional OT systems. And in fact, if we kind of throw a name at this, many of you probably know this name, right? We tend to talk about this concept as creating a unified namespace. And all that really means is creating a contextualized repository of data for all this information around your operations, your assets, and your procedures. So that's a kind of a key word there that the industry really uses to try to capture what we are trying to do, and with a lot of customers rather trying to do with MongoDB. Okay, so why MongoDB for the unified namespace? Well, really MongoDB, the value we bring is we bring the capability that is an operational and a flexible operational database that can store all these different kinds of data: the telemetry, the time series data, the unstructured data, the drilling reports, the maintenance logs, the service manuals, the procedural information, flow network diagrams, manufacturing operations information. All these different and very varied kinds of information can be stored with MongoDB. And when you store your information in MongoDB, we provide capabilities with our database offering to allow you then to search, whether it's vector search for generative AI use cases, whether it's classic text search for text content, but also to then do analysis and mining of that data within MongoDB, because after all, we are a database, right? So if we really call out the benefits of MongoDB, this slide here really captures sort of the kind of 8 key points here. And I'm going to build it out here just to let everybody kind of digest it. To me, the biggest value we bring is that we support a flexible data model. I'll talk a little bit more in detail what that means, but basically at a high level, it means we can support time series, daily reports, text, service manuals, all these different kinds of data. That's how we do it. Asset hierarchies, things that are really hard to do in traditional databases, you can do natively and easily in MongoDB. We have a first-class support for time series data storage, so telemetry can be stored in MongoDB efficiently. We've designed the database to do it efficiently and effectively. Vector search for generative AI use cases. So not just full text search comes out of box with MongoDB, but also vector search. So you can do those powerful capabilities like natural language query of your data for your business users, or querying through service manuals to identify the right service manual to pull up for that predictive maintenance use case to hand off to that technician to follow. A run anywhere model. MongoDB doesn't just run in the cloud with Atlas. You can run it on-prem, you can run it self-managed with our licensed Enterprise Advanced. You can even run it all the way down to IIoT class hardware with the MongoDB Community Edition. So we run everywhere in your stack. That creates a unified experience, a unified tech, and it really reduces the engineering burden to onboard MongoDB. And of course, we have some other capabilities here on the right there that are also important. I'm not going to drill as deeply into them other than just to call out MongoDB is infinitely scalable, not just vertically with bigger servers, but horizontally with more servers. That way you can always dynamically adapt your MongoDB database to the use case at hand. You add a new site, you bring a new site online, you can just elastically grow MongoDB to accommodate that. And then finally, enterprise high availability and security. Customers across many different industries use MongoDB for business critical operations, and our database is designed to provide an ultra high level of uptime and resiliency. That way your business doesn't go down. So here's a quick sort of almost a cartoon, if you will, very simplified model of how you might leverage MongoDB in a unified namespace. We have a site where we have various assets. I'm not going to model the entire Purdue model, the SCADA network, the OT network, but you create an integration from your OT network into your IT network over here. Notice at the top, in this particular case, we have the manufacturing and ERP contextual stores. We have integrations in this particular design via MQTT, just as well as the telemetry coming from the site is also being integrated for MQTT. And they're integrating continuously into MongoDB Atlas. That way we can perform data classification, obviously store the data, visualize the data, potentially traverse the data if it's graph, like if we have a flow network or model or something that we want to, or an asset hierarchy that we want to understand. All those can be stored natively in MongoDB. So quickly, so I can get back to Daniel, let him get into the demo here. The real key that I touched on a second ago is that idea of that document Mongo and with MongoDB. in my opinion, it is the single most powerful capability we bring to this space that really differentiates us from all competitors. It is really why we're getting a lot of traction with our customers. You can imagine you have a world today, this classical pyramid here of all the different levels of data from the OT and into the IT side of your organization. Uh, you need to contextualize that data together, right? Because you have data coming from many disparate systems, and it can come via many different protocols, industrial protocols, like here we see OPCUA, Modbus, etc. And you often want to create these very rich hierarchies and rich contextualized trees of information. And so with MongoDB, that's as easy to do as by creating a JSON-based document model. Again, everything in MongoDB with the document model is JSON-based, which really ties in well to a lot of the data we see in industrial space. We can contrast that with traditional databases that break everything up into tables. And the benefit MongoDB has is we model and represent the data more naturally. It means it's faster to access, it's easier to store, and it's much easier to change. This on the left-hand side is the old way of dealing with data. It's also why traditional databases can't do time series, unlike MongoDB, where we can do it as designed. Another quick example here, kind of bringing that home a little bit better. You can imagine if you had a catalog, an asset catalog. You've got concepts here. If we're talking about oil and gas, you've got a concept here of a well, a pump, a fluid model. Maybe these are all representative of a particular catalog for a well site. And so here, this is the sort of hierarchy of information you might have in this catalog. You can represent that naturally and dynamically in a JSON document within MongoDB, as you see here on the right. And it also makes it super easy. If you add a new asset, maybe you add a tank or a battery to that site, you can automatically add that into this hierarchy here. And that's just as easy as adding another subfield to that JSON document. No new tables to create, super easy. And that really revolves around that central point of MongoDB, that our documents are universal. So again, as I was saying earlier, not just telemetry, not just structured information with asset hierarchies, but geospatial information, graph modeling, key value data, tabular data. Everything can actually be represented as a JSON document and thus a MongoDB document. And that's again what makes us so powerful and different than other databases. So in the interest of letting us, get on to Daniel and the demo here, I'm going to skip a few slide here, just really kind of close out with some of the customers I've, worked with. A few of these I haven't, but just a sampling of some of the customers. We have quite a few more, some of which don't let us use their logos. But here's a sampling of some of the customers that use us for industrial data, some of them very much digital transformation use cases. Personally, I know of Halliburton, Corva, and Toyota, as I work all those accounts at one time or another. So that MongoDB is very much used for large enterprises, for business critical applications, and certainly for very large at scale applications dealing with a lot of disparate data types. And I think no better example actually is talking about computer vision and a lot of the visible spectrum data and imagery data that Voxel51 deal with. And also, of course, their tie-in that using MongoDB, I think is going to be very interesting as well. So, Daniel, I'm going to go ahead and hand it back off to you. That way, you can start showing some really interesting things with Voxel and hopefully really get some cool visuals.
Thank you so much. Appreciate it. Great handover and great talking about the data as well. We're going to go right into that in a second, talking about the data model and why MongoDB is really the go-to solution for all of this. So quick introduction to 51. If you haven't seen 51 before, I don't know how many people here have. I'll show you a quick little demo of kind of what it looks like and kind of what we'll be getting into. But if you haven't ever seen computer vision data, 51 allows you to kind of visualize all these different pictures, store those classifications, as well as what other potential computer vision annotations, model predictions, annotations, detections, segmentations across any modality, right? Not just images, but video, 3D, infrared, X-ray, basically any visual type of sensor, Voxel51 and 51 can support. And there's a lot of really cool workflows that we're going to go through, such as embeddings, which allow you to find like related samples based off model predictions, things like model evaluation, which allow you to see the overall performance of your model, but not just on one class, but on each individual class and on anomalies versus non-anomalies. And we're going to keep a manufacturing theme around this all. So let's go back into our slides, and I'm going to give you a little bit of an introduction here. So how did it all start? Well, we were built on MongoDB from the start. We're founded by a professor and student combo. That is Brian Moore on the left and Jason Corso, professor from University of Michigan on the right hand. They started a company more than 5 years ago, but they started the open source tool 51 5 years ago, all with the idea of making data better, right? We have so much data today. And if we really want to be making our model as best as possible, it doesn't always lie. In fact, most times today, it doesn't rely on making the actual model architecture better. You just have to make your data set better because all those mistakes, outliers, and more that we will find later on today is really what is going to drive that data set performance down. So how did this come up? How did we start working with MongoDB and kind of built this idea? Well, they were actually reached out by GM and Ford about 5 years ago to help manage this problem that they had. They wanted to help work with some of their driving data, things like, self-parking, lane assist, stuff like that back in the day. But Ford and GM had so much data and they couldn't actually work with it at scale, right? They needed to visualize model predictions, visualize ground truths, and kind of be able to sort through this in an efficient fashion for people to begin working on it. And there was two main things that were always true, no matter what type of problem they were working on, is that in enterprises or in commercial experiences, the data is always going to be unstructured for visual. Visual data is naturally unstructured. You can't shove it into a table. And the other one is that it is a huge scale, especially with these self-driving, these manufacturing customers. They are working with petabytes of scale potentially. And you think about it, and Robert touched on this, the manufacturing line is running potentially 24/7, if not 18 hours a day, 20 hours a day. Every single thing that comes off the line is getting a picture taken of it to verify integrity, to make sure that it came off the line, to make sure that there's no issues with it, all these kind of things. Well, do the math. If that's 18 hours a day over 365 days over the last 5 years, I mean, you're looking at tons and tons of data, more than you could ever picture, or really importantly, more than a human could ever scan through in a reasonable lifetime, honestly. So how do we deal with this problem? Well, let's first talk about why it has to be MongoDB, why we can't, solve this problem with tables or tabular tools, SQL and things like that. We're looking at a very easy example here where in my same data set, I have the picture on the left of the bear and I have the picture of the right of the crosswalk. On the left, I have one detection. There's just a bear in the photo. I don't really need to have any more computer vision metadata for my model to understand, other than that there's just one bear. Secondly, this picture, I have a ton of detections, handbags, people, purses, umbrellas, and more. You can see I have to have a lot of different spots for every individual detection that I have in my table here. And so you can see for sample one, I only need one, but for sample zero, I only need one, but for sample one, I need a ton of rows. This is why I don't want to be wasting all of this space. My table shouldn't have to be as long as my longest sample. That really kind of bogs down your database. Another way to visualize this, and this is the truth, we were talking about how everything in MongoDB is kind of JSON formatted, and you can kind of compress everything into JSON, so it's very efficient. This is all the information I need for the first image in JSON form. You can see it's just a nested list with a detection object. All this can be serialized into a JSON that goes into MongoDB on the back end. This is all the information I need for the other picture, right? I mean, we can't even read that. It's lines and lines and lines and lines and lines and lines of text and metadata and code, all to represent all the intricate details I need to teach a computer vision model on this second image. So this just makes tables impossible. We have to use a tool. And luckily, MongoDB is perfectly built for these kind of use cases. As Robert mentioned, the data that comes off of industrial use cases, off of manufacturing lines, off of computer vision problems, tends to be unstructured and naturally fits together. So this is why Voxel51 kind of set forth to kind of help build on top of MongoDB to make a visual front end, to add in real computer vision algorithms to help annotate and curate your data set, all with helping you evaluate to make sure that at the end of the day, your model is going to perform to the best ability possible. So what we're going to talk about, I want to make sure that everyone here kind of understands how 51 makes computer vision projects better. I want to make sure that everyone has a chance to get your hands on with open source 51. I'll get some code examples that everyone can try out that goes through some manufacturing use cases. And I want to make sure that everyone's set up with a solid foundation to go after this talk, right? So we're not going to be able to cover every line of code today that I have in some of my examples that I'm going to show today, but I do have enough kind of paths for you to go down if you are curious to learn more about maybe a specific thing or take this home with you to try on one of your own projects. We're going to have plenty of opportunities for you to kind of branch off here. So first, let's define kind of what visual AI is. And we've been throwing out these terms computer vision and then visual AI. All you really need to know is that visual AI is kind of that natural evolution of computer vision, right? And terms kind of get thrown around. Physical AI is often thrown around nowadays. But the reason why we use the term visual AI compared to traditional computer vision is a lot of traditional computer vision is thinking things like edge detection, Fourier transforms. We think about even ImageNet. We still think of classical computer vision, but now visual AI is a lot more. It's the data set side of things. It's the modeling side. It's the deployment side. It's Gen AI. It's visual question answering. It's how LLMs interact with visual prompts and things like that. And this all heads into kind of this enhanced visual AI capability of how can we make these machines really perceive the world in a visual context in the most modern way possible. So if you ever hear the term visual AI, just think about it as like an upgraded computer vision, if that makes sense. Moving on, what are the common pain points? We kind of talked about this a little bit before. If you haven't dealt with this in production, that's awesome. But 80% of AI projects tend not to work, right? Whether it's the model doesn't go, it can't be deployed correctly, it was more of just a POC. 80% of projects tend to just fail in production. Why is this the case? Well, a lot of time it's because of this model-centric approach. We invest so much money in getting a data set annotated. We spend all this GPU money to train a really big model. We deploy it, and then we find that once it's deployed, there's all these cases that we just didn't really think about, right? And now we have to spend this really expensive cycle to go back, try to solve these problems, all with the model at the focus of, oh, how can I make this model better? How can I make this model better? And that is going to lead to a lot of problems. And what can these problems actually come up? One of them is model bias issues, very serious, especially when it comes to human interactions, that we want to make sure that we have all cases represented inside of our data set. Additionally, it can actually lead to real lethal physical danger. There was a case a couple years back of a Tesla car went off the rails, went too fast, and there were people that were seriously hurt during the crash, and some people have unfortunately lost their lives. So we're way past the point where these things are just fun in a lab, right? This is real world consequences. There's self-driving cars in the street today, whether it's Teslas or Waymos or whatever car you're using, as well as many more being deployed in manufacturing lines, that these machines are very dangerous, the robotics are very dangerous, and we have to make sure that everyone's safe in this process. And then lastly, of course, we just want to make sure our model is not getting a reduction in performance. If there is good data being left in our data set that's not being taken advantage of, we want to make sure that we get that all the way in front of our model. And we want to make sure any poor data is pushed to the back, submissed, and fixed really before our next training run. So moving on, like I said, our goal now is not to build a better model. Our goal is to build a better data set. With a better data set, everything will come after, but sometimes this can feel like a difficult task. And I'm here to show how with 51, we can kind of move over to this data-centric approach, focus on data set quality, focus on reducing our bias and errors, and ultimately get to a much more cost-efficient and more performant way of building AI stacks out. So AI stacks isn't just about better models, it's about better data sets, and that's what 51 is all about. Today, 51 is the only open source data-centric AI solution that allows you to curate, visualize, and analyze your data set. We'll be going through some of these workflows, such as streamlining annotation workflows, finding and fixing labeling mistakes, identifying and correcting model failures, all to help make 51 make your visual AI more of a reality. If you're familiar with visual AI tasks, we support almost every single one from classification, detection, instance segmentation, semantic segmentation, all the way to the more complex ones for multi-view, multimodal, anything that's an image, video, or 3D problem, we at 51 can help you kind of solve that. So if you're trying to understand where we fit in everything, It's all about in the very upstream task of you have a data set, you have data, maybe it came off a sensor, maybe it came off the manufacturing line, maybe it came off a car, maybe it's off of a robot, whatever that is. Uh, After that step of it lives somewhere on your computer, if it's open source, if it's in your cloud for enterprise, it's all about helping you integrate with the products that your company is using throughout your stack, helping you compare and evaluate models, kind of visualize embeddings to find outliers, and really help you kind of load and filter out that data set so that we're only using what is most important for us. And we'll look at examples of this in a second as well. This kind of forms a common lifecycle inside your stack where you are bringing in new data, correcting that data set before training, splitting it up for that next training run, training the model, evaluating the model to understand where the weak points are, what scenarios does it fail on, what subsets aren't represented well enough, and then we can then validate that and then push it into our next data set start. And we start back at step one of getting more data, cleaning, curating the data, and then starting off more. This allows us to have a much more flexible life cycle in production where we're not putting all of our eggs in one basket when it comes to this one model that is deployed in production today. And then we have to wait for another model life cycle, maybe months later, in order to get a new one into production. This allows us to kind of rapidly keep on redeploying. If a new model architecture comes out tomorrow, which there's new model architectures coming out almost every week nowadays, we can rapidly kind of just pull that off the shelf, plug it into our existing framework, train it on all the data that we already have ready, and then go right ahead and compare that to the existing model. Instead of having to do the opposite, where if a new model comes out, we now have to redo all of our data set stack because all of our scripts were trained and built and for the previous model. How can we pivot fastly? By putting all the investment in the data set. That's really where you're going to get the best bang for your buck in ML training nowadays. So let's look at some hands-on experiences. I have a link here, QR code. I believe Kirti is also going to drop a link to the GitHub page. In this GitHub page is a series of notebooks. I will show you kind of what it looks like. If you go into this awesome 51 from my colleague Paula here, we helped build this getting started notebook guide where we're going to have notebook 1, 2, 3, 4, 5, 6, 7, all the way, all talking about manufacturing here. We're going to, of course, start with number 1. But as I go through further and further through some of these talks, I'm not going to necessarily jump into the code every time, but I will reference it to, hey, if you want to try this yourself, it's available in notebook 3, 4, 5, essentially. So without further ado, let's just hop into 1 then. So we are going to start by loading and exploring a data set. What data set we're going to use? We're actually going to use the MBTech AD data set. It's one of the best data sets available for manufacturing today. It might not work. It might not look exactly like your problem. It might be slightly different, but all the techniques, methods, curation, filtering is all very applicable to whatever problem you're working on, right? Especially if you're working in anomaly detection use cases. So in this case, like I said, it might be wood, screws, nails, and transistors, and your problem might look a little bit different, but everything can transfer over in this case. So in this first one, we're just focusing on kind of getting our hands on understanding what is happening here. Here it says pip install 51. You don't have to use this version. You can use any of the newer versions and such. This is just a guaranteed version, so we know it works. But feel free to use the latest version as well. I tested it today. It still works. So we're going to start off here. There's a couple ways you can load data sets into 51, and there's a nice link here to help you understand how you can do that yourself. But there are a lot of publicly available data sets that we have already kind of formatted for testing purposes, demos, learning the tool. And one of those is that MBTech AD data set. So here we can load it actually straight from Hugging Face. This data set exists on Hugging Face in 51 format, and you can kind of pull it right in. We call this load from hub function. And this is going to load our data set. We are then going to name our data set. And this will tell us if it exists already or if we're moving a new one. So in this case, I do know my data set currently exists. I don't have to load it in. So I can skip this line here, and it should just work for me. There we go. From there, we can start printing out some information. When you go to explore your data set, and as I mentioned, we're always going to link off to the documentation here. But as you begin to explore, you can always print out that data set, and it's going to give you a summary of all the stuff inside of our data set. So I can see some really interesting things off the bat, such as that there's 5,354 samples. A sample is an image in this case. And we have all these different fields. So I see it comes preloaded with a defect, defect mask, and the category as well. You can also print out the last sample or the first sample in your data set by just typing in dataset.first or dataset.last. And this will give a nice snippet into what that sample looks like. You can see here that the file path is referenced. This is because everything in 51 is logically related. We're not copying your samples. We're not reinventing the database. All we need to tell Mongo is, hey, this is where the file lives. And then 51 will handle the visualization of that file. You can also see some of the other things here where we have some fields, such as the classification of our category, such as the defect found, as well as the defect mask or the location of the defect on the image. Now, the awesome thing about 51 is it comes with a pre-built app that allows you to visually inspect this. And this is what we were looking at a second ago here. So if I go back to my Google Chrome, you can see I'm just at a local host address here. And this is what the data set looks like after you launch that app. So you can begin clicking through, looking at our transistors. You can see that we have some good transistors here. In fact, without going crazy on my scrolling here, I can see that these are actually all good transistors. But that's not exciting. We're here to find defects. I can sure enough tell you that this transistor looks good. I want to know if it looks bad. Well, I can very easily kind of go over into my label here and begin looking at all the different types of defects that we have inside of our data set. So I can click on bent lead, for instance, and sure enough, here are all my bent lead transistors in my data set. I can look for a different one. I can look at broken. And we're going to see, oh, wait, I actually have some other data set points in my data set. And maybe this is something that we didn't know or we're interested to find out which ones are. So we can always head over to our categories and see all the ones that we have. We have bottles, for instance. We also have some capsules for medicine. We have a metal nut that is going to have some defects on it, and many more, such as hazelnuts, transistors, wood, zippers, hopefully something that can relate to your problem that is somewhat similar, whether it's electronics, some steelwork, or something else like pharmaceuticals. So you can see how you can rapidly begin filtering on any of the metadata that you've stored in that sample. Now, if you're more familiar with MongoDB than you are familiar with 51, for instance, or computer vision, you'll start to kind of piece together what's happening here, right? Which is each one of these is kind of the ground truth document. And we have stored metadata on top of this document. In fact, I can actually look at that JSON view that Robert was talking about in the app to see exactly how it's laid out here. Now, based on how we've stored information on the document, I can then now filter that in our app right here, whether it's something that you've provided or maybe in the future, in your cases, something that your model or an AI has predicted on top of your data set for you. We can also see the segmentation masks if they're located, if you have them. I believe that some of these might not be present on the transistors, but when they are poorly misplaced and such, in case of this one always cracks me up. It's just completely missing. So you're always able to kind of see where that defect is happening. There's a lot more exciting things to look at. But let me go back into the code here. So notice here that we just called to launch the app. Auto, that just means don't bring it up in my notebook. Just I'll go to the local host. And by default, this port is 5151. But you can make it whatever port you want. And then just open that to your local host, and you'll be able to see that. And some pictures here of what it should look like. But we're going to look at querying and filtering. And this is really where the curation part happens here. Sometimes when you go to train for computer vision, we're training on everything. Sometimes when we go to computer vision, your boss tells you, dude, I don't want to see the transistors today. Train a model on everything but the transistors. And you're going to have some unique problems here where whether it's a new type of training set or something you're interested in evaluating, we need to remove and kind of hone in and filter our data set to kind of find samples that are very important for us. Well, it's very easy to do that in 51 with our view system. Now, there's some really good documentation here as well, But you can begin to understand things like, okay, well, we just saw previously in my app, if I go right back, that we have this label called defect. And we know that our defect has a bunch of different things on it. Well, if I go back to my code, I can actually find every defect in my data set that is a scratch. How do I do this? Well, I say data set, match, scratch, right? And this view field is basically looking at the defect label and to see if it's equal to scratch. Why is this the case? Without getting too into the weeds here, we don't have a field in Mongo or in our data set that is a Boolean, hey, is this equal to scratch, essentially. So this is how we can talk to 51 and how we can talk to Mongo and say, hey, if it is equal to scratch, then bring it up to me. What we can do is we can run this. We can see that we went down from 5,000 to 91. I go back to my app. You can see it's updating for us. And now we only have scratches in wood. So we can see that we have exactly what we were looking for. We also have some scratches in some of our pills and some scratches on our nut as well. Now I can go back here. This isn't the only type of filter that we can do. We have more. We can look at only the categories for wood. You can see that we only have wood then. And we can do even more interactive things through plugins, look at graphs, create new data sets, export this data set, send it to a colleague, and help you understand. I'm going to go back to my slides here, but this is a nice little tutorial on how it means to load in a data set, work with the app, and how you can use views to kind of really narrow in what you're looking for. Also, I just want to stop here real quick. It doesn't look like we have any, but if there are any questions in the chat, feel free to drop them in the Q&A. I'll be happy to answer them at any point. I want to make sure that anyone's lost here throughout. Let me skip ahead here. We just talked about Notebook 1, but I want to talk about some high-level things about this. Not this, we talked about this. In terms of the architecture, because we kind of skipped over this in the beginning, is the MongoDB portion is the backend. It's all the dataset storing, the indexing, queries. You can even integrate this with your Mongo Atlas if you're a Mongo Atlas customer and really leverage the vector database side of it too. In the middle is the 51 SDK that allows you to create datasets, run computer vision algorithms, and help you build model architectures inside of 51. And then the front end is that app that we were just looking at, such as visualizing the environment, interacting with your samples, and kind of kicking off new jobs and such from there as well. From there, there's many different types of data sets. There's things like image data sets, videos, 3D, or group data sets even, as well as many different labels. But the important thing to kind of understand is that all of these things live in one place. So whether it's sample metadata, such as file path, dimensions, the time of day it was taken, where it was taken from, what plant this came from, embeddings, features is your real ML heavy stuff, or things like similarity search or feature vectors. The annotations and labels of your data set, as well as your model predictions, all can live inside of the one data set. And we can compare and contrast and use each one of these to help drive different insights inside of this. From there, you can kind of understand the data set structure. And if you're familiar with Mongo, this should also be familiar to you, where at the very bottom, we have our data set collection. This holds all of our samples of images or videos. The sample is that atomic unit in this case. It can be a file path to an image. It can be a video. It can be a 3D point cloud. And then we're going to store a bunch of fields on top of that sample, such as the annotations, as in the Mongo, such as annotations, such as labels, such as model predictions, such as metadata, all that kind of stuff. We looked at some of this, but you can kind of see the different labels, defect, and mask path that we stored on top of our data set here. We also talked about some of this filtering already, so I'm going to skip through these slides. But it's very powerful to begin curating your data set to use things like match, filter, slice to help you understand. After you've kind of found that interesting subset that you're looking for, we call that in 51 a view. Basically, the data set is the parent. If I filter it down, I now give you a new view into your data set for you to work with. Now, a view in 51 functions in the SDK, at least, exactly like any other data set. There's only very few things where if I could do it on a data set, I could do it on a view. So if I want to filter a view, just like I filtered a data set, you can to get a more fine-grained approach. If you wanted to run a model and only use it on your view, you can do that as well. If you wanted to export only your view, you can do that as well. And then independent of that, if you're very happy with your view that you've created from your data set, you can then call clone, which is going to make it its own parent data set. So basically any change you make in a view will be reflected up to the parent, right? So that sample is permanently changed in the parent. But if you make a new clone of the data set, it's now independent. So any changes, images I add, models I add, valuations I run are now independent of that original data set to help clean up your structure and make sure that you're only working on the important things at once. A couple questions in the chat I want to make sure I get to before I move on. Looks like Robert beat me to the first one, so great there. The second one is any case study from transit in SAP. I can show an example towards the end of this conversation about transit and some other interesting ones there as well. But thank you for answering that question in the chat, Robert. That was very helpful. Let's move on. We're going to talk about embeddings. Now note this is notebook 2 in this case. I'm going to breeze through this because I want to make sure that I have enough to show it. But I want to show you that if you don't know how embeddings work, they are image to insight transformations, right? So I can pass an image into a model. It is going to create embeddings. Then we're going to run some dimension reduction, which helps it make more visual for us. And then we can visualize it. This allows us to enable a bunch of new workflows from things like similarity, overlaps, isolated anomalies, unclustered samples, and clustered samples. And this is an example of how to do it. I'm going to show you what it looks like in our data set. So I just have if anyone's confused where I went, this was my localhost one that I just loaded. This is the data set before any work has been done on it. I have in my enterprise version, which is just a URL that I go to essentially, a finished version that I have all the nuts and bolts, no pun intended, models loaded, evaluation runs, embeddings. I don't want to make anyone here sit through compute time or anything like that. And with our enterprise version, these things live on the cloud. It's super easy to access and scales very easily. So here what we're looking at, I have all my embeddings. If you've never seen an embeddings plot, congrats, this is your first one. And on the right, we can see that we've colored it based on the type of the defect. So for instance, I can grab all these and we will notice that these are all flipped nuts. They all look backwards essentially. I can go into a different category here and we can zoom in to get a more fine-grained approach. But when I grab these samples, we're going to find that these seem to be a mix of scratched and bent nuts in this case, I believe. But if it gets a little bit too confusing for us, what's really cool about the embeddings panel is I can actually turn on and off different types of anomalies. So this is where all my bents are. If I want to find where all my goods are, you can see that they're all kind of scattered around, which is what we would expect. We can see where all my roughs are, where all my scratches are, and so on and so forth, right? It's very easy for us to kind of hone into our data set and find exactly where we're looking for. Let me just refresh my page real quick. It's a little laggy. Now, the other interesting thing about embeddings is we can color them with any type of metadata that we've stored on our field before. So I don't have to just do them on defects. I can do them on the evaluations, whether they're a true positive or a false positive. I can do them on my model predictions. I can do it on the split, the defect, or even like the category, for instance. So if you're wondering why they were clustered like this in the first place, maybe this makes a lot more sense because we can see that down here, these are all of our bottles. Why are they all grouped together in their own color? Because all the bottles kind of look like all the other bottles. If I go over here to screws, why are all the screws over here? Because all the screws look like all the other screws and such. And we should even be able to see even more semantic differences, right? Where if I grab these screws, these ones all tend to be pointed up, for instance. Wild guess, are these going to be all pointed down? There we go. See? So we can understand how our data set is related, help understand these differences, and kind of help spot outliers. Now, this data set is pretty good and pretty clean overall. So there's not really much in terms of outliers in this data set. But we can kind of understand those differences that I mentioned even grab these things all the way on the right. And like I said, we saw up screws, we saw down screws, and wow, lo and behold, we can find left and right screws as well. You can see how these things are kind of related to each other. Let me go back to my slides because I want to make sure that we have enough time. If you are interested in trying that flow out, it's available in Notebook 2 here. But moving on, embeddings are powered by models, and we have plenty of models in our model zoo. So if you want to use models from things like OpenAI's Clip model, Dino2, SAM2, or other models that are available, they're all available through our model zoo, which you can kind of get out of the box with 51. And it will work on any sample that is compliant. We can then do some clustering. So we can see once you've loaded your data set in on the full MVTech AD, we can get into cluster. What is clustering good for? It helps us identify the different kind of structures in our data set if we come in with no assumptions, right? So imagine this is all unlabeled and it looks like this in your embeddings view. Well, then we can kind of begin to identify the different amount of classes potentially, or understand the different distribution inside to understand kind of where does the models, where does my prediction model potentially kind of see the different categories here. You might have some really interesting insights into it. You can also use embeddings to help find abnormalities, such as broken bottles, things like that. And in this case, with the broken bottles, we do have some outliers. As you get to the more broken large, you can imagine that makes sense. The bigger the break, the more weird it kind of looks, and it's kind of easier to spot. Whereas if you are familiar with how things like anomaly detections tend to work in production, we're actually really interested about the precipice, right? The kind of mesh zone here of some are good and some are not so good. Where do we draw that line? And is that clear to our model in those differences? Or maybe we haven't gotten a good enough camera angle or enough camera angles or lighting scenarios or other things that could help affect this kind of anomaly prediction. But really, embeddings are about helping us enhance machine learning. It helps us visualize, find similar samples, identify leaks in your training splits, help you find duplicates in your data set. Duplicates can really drive down the performance. Even removing, I think, 1% of duplicates from a data set can drive model performance up by like 50% or something like that, potentially, just because it's a form of cheating. Uniqueness, mistakenness, hardness, and representativeness are also really important characteristics of a healthy ML data set that is driven through an embedding. Lastly, one of the last categories before I want to stop for questions and make sure that we have enough time to wrap up here is model evaluation, where with 51's built-in model evaluation panel, we can begin to compare and contrast multiple models and their performances on your data set. In this case, I can hop over. I can go and check out this demo. In this case, I have the model evaluation pre-ran on this data set. I can see the overall summary statistics. I can see the metric performance, such as precision, recall, and F1 score. The class performance, we can see our precision seems to be pretty high for our diffusion. And we can also see our confusion matrix. Now, what's really fun about all these graphs is they're all interactable. So you can see in this case, I have 10 that were labeled normal, but are actually anomalies in this case, based on our prediction. And we can see here that this is a completely normal nut, but it was labeled anomaly, and I'm curious about that. Likewise, I can see the opposite, which were labeled normal, but are actually anomalies. So this is a really good way to help us understand kind of why this is the case, help us drill in where our model performs the best, and we can even compare this against multiple models, right? So if you have a different type of model, such as patch core versus pattern, we can actually see that model performance comparison across the different metrics as well. Super powerful, allows you to really nail in and identify new things. You can even begin to kind of identify specific scenarios. For instance, the actual individual object category you can classify. And so now I'm not only looking at things like the class, but I can look at bottles, muddle nuts. You can have bigger buckets here, smaller buckets. You can do this based on plants that are happening it. So maybe you have a Texas plant and you have a California plant and you have a New Jersey plant or whatever it might be. Now I can compare not just, the model performance across every plant, but model performance in specific plants. And I don't have to rerun the evaluation to do this. I'm just doing this through our evaluation panel. So it's very powerful and really helps us kind of drill down problems. Hopping back into my slides, we have a couple questions I want to answer. The first one is, how is hardness measured? Hardness is measured based on I believe, the form that we use. It's open source. You can check out the algorithm. It is a method that looks at the embeddings of the classes and then tries to decide based on how close this class looks to the rest of the classes in the data set. So basically, another way of saying that is like if you have a cat data set and you've labeled every type of cat, if you have a hairless cat, that might be a more difficult problem if you were just labeling cats, for instance, because hairless cats don't really look like all the other cats in the world. But if you had a hairless cat class, then that class should be pretty easy, and I wouldn't expect there to be hard samples in it, for instance. I hope that makes sense. Someone else asked, can you elaborate how the near duplicate detection is done? Yes, absolutely. Duplicate detection is done in two ways in 51. Near duplicate detection. If I go into my embeddings view here, I can show you some examples where you would imagine, if I look at my entire plane here, all these are kind of separated from each other. If I really zoom in, we can still see that there is some level of kind of gaps between them. If these two dots were like essentially on top of each other, that's a near duplicate. It's either it's actually a duplicate and it's just a little bit different, or it's like, hey, we're shooting a video at 60 FPS. You can't train on every single frame. You're going to be like cheating your model essentially, right? We want to make sure that that is the case. We're shooting on 60 FPS, that every other sample in the data set is shooting at 60 FPS, right? And it's sometimes better to take keyframes from there. That way our model is just learning the differences and doesn't begin to cheat based on overfitting and things like that, for instance. So that's near duplicate detection. It's overlapping embeddings, essentially. They're nearly exactly the same. A exact duplicate is based off the hash. This file is exactly the same hash size as that file. This is an exact duplicate. You know, it's essentially the same file path, if not literally the same file path. It's okay though, mistakes happen and duplicates are very common in most data sets. So I'll end here, open up for any more questions. I have all my links and QR codes here. Last thing I want to say, you know, everything I've been showing you here, some of it is open source, all the 51 stuff, all those notebooks, everything can have a hand on it. The demos I was showing on the other side are all in the cloud. Why? Because we want to make sure that we have something that's very easy to access, that we can share across our team members, scale up to the petabytes of data you're potentially working with. Open source is only going to run on your computer, right? It's meant for a single user, for research, PhD students, small teams of like 4 or 5 engineers. But as you really begin to scale up, especially if you begin to scale up with Mongo, scale up with Atlas and vector search, and you have more and more tools kind of get built into your ecosystem, Enterprise is a really interesting thing to check out. And I highly suggest you, if this has resonated with a lot of you, that you kind of check it out in browser or you book a demo and we can help you out. Otherwise, on the right side, we have that GitHub repo to that, all those examples that go into embedding workflows, evaluation, all this kind of stuff and more, as well as the documentation to the core 51 open source. That'll teach you on how to load in your first data set, build your first data set, evaluate, and more. Hang on for a couple more minutes. Robert here as well, if you have any questions for him. I'll leave it on this page. One last note, also just kind of happy to, I thought I had it up next, but happy to connect with anyone on LinkedIn if you'd like. You can just look up my name and be there. I'll find you and stay in touch. If you have any questions about 51 or anything like that, I'm always here to help. Looks like we have no more questions for now. Hang on for one more minute. Oh yeah, let me drop my LinkedIn too. Now that I have a free second. All right, looks like we have no more questions. So I'm going to sign off here. Thank you everyone who joined today. Really appreciate you taking time out of your day. and helping us, facilitate here. You guys have been a great crowd and asked some great questions. And I hope everyone is successful in all their endeavors, whether it's in computer vision, MongoDB, or some other computer science, or any real field anyway. And I hope everyone has a great rest of the week as well.
Thank you all. It's been a pleasure.